Hello and welcome, cosmic explorers, to a journey that will challenge your very perception of reality. Today, we are venturing deep into the heart of modern physics, to the bleeding edge of theoretical cosmology, to confront one of the most profound and unsettling ideas ever conceived. It's a theory that suggests our entire universe, with its trillions of galaxies, its beautiful nebula, and our own precious blue planet, might be living on borrowed time, balanced on a knife's edge between existence and instantaneous total erasure. At the center of this cosmic drama is a particle you've likely heard of, one with a name that carries an almost mystical weight, the Higgs boson, famously and controversially dubbed the God particle. Now, when the Higgs boson was finally discovered in 2012 at the Large Hadron Collider, it was a moment of triumph for science. It was the final missing piece of the standard model of particle physics, the elegant theory that describes the fundamental forces and particles that make up our world. The primary job of the Higgs boson and the all-pervading energy field associated with it, the Higgs field, is to give mass to other elementary particles. But how does it do that? Imagine a crowded party, a room filled with physicists. Suddenly, a huge celebrity, let's say Albert Einstein himself, walks in. As he tries to move across the room, he gets mobbed. People cluster around him, slowing him down, making it hard for him to move. This resistance to movement is, in essence, mass. In this analogy, the partygoers are the Higgs field, and Einstein is a particle like an electron or a quark. Particles that interact heavily with the Higgs field are like a major celebrity. They acquire a lot of mass. Particles that barely interact, like photons of light, are like an unknown person who can zip through the room unnoticed. They remain massless. This discovery was monumental, confirming decades of theory. But as physicists studied the properties of this newfound particle, particularly its mass, which clocks in at a very specific 125 giga-electronvolts, a chilling possibility began to emerge from the equations. It seems the God particle, the giver of mass and substance, might also harbor a dark secret. It might be the key to our ultimate undoing. To understand this, we need to talk about the vacuum of space. When we think of a vacuum, we imagine pure, absolute emptiness. But in quantum physics, the vacuum is a far stranger and more active place. It's the lowest possible energy state of the universe, a seething soup of quantum fields fluctuating in and out of existence. The Higgs field is special because, unlike other fields, its lowest energy state isn't zero. It has a baseline value, a non-zero energy that permeates all of space-time. This is what we call the vacuum expectation value, or VEV. This is the normal state of our universe. But what if it isn't? What if what we perceive as the stable ground floor energy state of the universe is actually a cosmic illusion? Think of it like this. Imagine you live in a beautiful, serene valley surrounded by gentle hills. You believe this valley is the lowest point on Earth, the ultimate point of stability. But what you don't know is that just over the nearest ridge, there's another valley, one that is miles deeper, a place of far greater, more profound stability. Your valley isn't truly stable. It's what physicists call metastable. It's stable, but it's a false vacuum. It's a precarious state, and the precise measured mass of the Higgs boson in relation to the mass of another particle called the top quark suggests that our universe might be in exactly this kind of metastable false vacuum state. It implies that there exists a true vacuum out there, a state of much lower energy that the universe falls into. So, what happens if our universe, resting precariously in its high-altitude valley, suddenly gets a nudge? What happens if it finally tumbles over that ridge into the deeper valley below? That terrifying question brings us to the ultimate doomsday scenario: vacuum decay. We've established that our universe might be in a metastable state, a false vacuum. To truly grasp the terrifying implications, let's return to our analogy of the valley. Our universe is like a ball resting in a small dip on a mountainside. not in the deep, vast valley floor far below. That small dip is our false vacuum, and the deep valley floor is the true vacuum, the universe's preferred lowest energy state. The only thing keeping the ball from rolling down is a small hill, an energy barrier. In classical physics, the ball would need a significant kick of energy to get over that hill and begin its descent. But our universe doesn't play by classical rules. It plays by the bizarre, almost magical rules of quantum mechanics. This is where a phenomenon called quantum tunneling enters the picture. It's one of the strangest predictions of quantum theory. Imagine throwing a tennis ball against a solid brick wall 1,000 times. Every time it will bounce back. But if that tennis ball were a quantum particle, there is a tiny, non-zero probability that on the 1,001st throw, it would simply appear on the other side of the wall without ever having broken through it. It tunnels through the barrier. Now apply this to the entire universe. The universe's energy state, our ball in the shallow dip, doesn't need to be kicked over the energy hill. It could, at any random moment, in any random location, simply tunnel through the barrier. If this happens, a tiny bubble of the true vacuum would spontaneously nucleate, appearing out of nowhere in the fabric of our false vacuum. And here is where the true horror begins. This isn't a localized event. The moment this bubble of true vacuum forms, it starts to expand. And because the true vacuum is a lower energy state, the transition releases a colossal amount of energy at the bubble's boundary. This energy fuels the expansion, pushing the bubble wall outwards in all directions at the absolute maximum speed possible, the speed of light. There would be no warning. No telescope could ever see it coming because the light from the event would travel at the same speed as the wall of destruction itself. One moment, the Andromeda galaxy is 2.5 million light-years away. The next, it's simply gone, converted. But what does converted even mean? This isn't like a supernova explosion which obliterates matter. This is far more fundamental. As the bubble wall sweeps through a region of space, it rewrites the laws of physics. The value of the Higgs field changes catastrophically. This means the masses of all elementary particles, electrons, quarks, would instantly change or vanish. The fundamental forces that govern reality could be altered beyond recognition. The electromagnetic force that holds atoms together, the strong nuclear force that binds protons and neutrons, they could shift in strength or disappear entirely. In this new, true vacuum universe, the laws of chemistry and physics as we know them would cease to exist. Atoms would fly apart, stars would be extinguished, planets would dissolve. All complex structures, from the largest galaxy clusters to the very neurons firing in your brain, would be instantly and silently converted into a new, stable, but utterly unrecognizable state of matter and energy. It is the ultimate form of erasure. It is not death. It is the deletion of the very possibility of what we call life and existence. The finality is absolute. So, should we be building cosmic bunkers and living in constant fear? Thankfully, the answer is no. While the theory is mathematically sound based on our current understanding, the calculations for how long our metastable universe could last are mind-bogglingly vast. The estimated lifetime is not in billions, but in trillions upon trillions of years, a number so large it's many orders of magnitude greater than the current age of the universe. The chance of it happening in our lifetime is so infinitesimally small, it's practically zero. Furthermore, these calculations depend on precise measurements of the Higgs and top quark masses, and as our instruments get better, these numbers could be refined, potentially revealing our universe is more stable than we thought. Still, the theory of vacuum decay serves as a profound and humbling reminder. It reveals a universe that is far more dynamic and potentially more fragile than we ever imagined, a cosmos balanced on the razor's edge of fundamental constants. So, what are your thoughts? Is the concept of vacuum decay a fascinating piece of theoretical physics or a genuinely terrifying cosmic possibility? Let us know in the comments. Subscribe for more mind-bending science, and we'll see you in the next one.